So welcome to the propulsion class. Again, we are going to start chapter 4 today. We talked about the example problems from chapter 3. Hopefully all of the confusion is gone by now. If not, please send me an email or come to my office, we can talk. But chapter 4 is essentially going to focus on the components of a turbojet. We are going to talk just a little bit about the main components of a jet engine, which is the gas generator, and then we will go into a gas turbine jet engine, which is like one of the earliest models and one of the most common models of a jet engine when you're dealing with subsonic flow. Which will, I think this part, the aircraft gas turbine engine, will take us 2 lectures. So this lecture and the next lecture on Monday. And then we'll move on to the mixed exhaust turbofan engines with afterburners and turbofans, other types of engines, which means that we are going to be done with chapter 4 by next Wednesday. And you will have a quiz on chapter 4 material on Friday. I try to solve some examples for you with the lecture, the book examples, but I will also post I'll make sure to solve some examples that you to make you ready for the quiz. I will also post the homework on sometime this week, right before the end of the week, which will be due next Friday, for example, before the quiz. Okay, is there any questions? Okay, gas generators. Gas generators are essentially have 3 different components: compressors, burners or combustors, and turbines, right? This is what a gas generator looks like, and it is also worth mentioning mentioning the fact that we are going to do a cycling analysis. So most of this chapter is going to be a thermodynamic analysis, and which you are familiar with a little bit. We are just going to apply that knowledge to turbojet engine. Okay, so a turbojet engine has an inlet. The inlet part is, let's say, a gas compressor, not a turbojet, a gas generator. So we have a compressor, burner, and a turbine, and this is going to be your HS diagram. Let's say your compressor inlet is at station 2. You start at station 2. You have an enthalpy and entropy increase to station 3. Then in the combustor, you have a 3 to 4 enthalpy and entropy increase, and then you will lose some of the enthalpy in turbine, come down to station 5, and then from 5 to 2. This is an open cycle, so the 5 doesn't really connect to 2, right? It's not a closed cycle. Okay. So, let me ask you this. Why do you think we lose some of the enthalpy into turbine? Or what does it mean? Let me start with this. What does it mean when we are adding enthalpy in a state from 2 to 3 and 3 to 4? What does it mean?
2 to 3 is just as you're compressing the air, it's heating up.
Okay. It heats up. Does everyone agree with Ryan that the reason behind the enthalpy increase is the gas is heating up? Just think about it. You don't need to just think about it. What's going to happen in a compressor? What kind of a process we have in a compressor? So when you say it is heating up, what does it mean for the process that is happening in a compressor? Like, we have how many types of processes do we have in a thermodynamic cycle? Thermodynamic processes. We have a constant pressure process, isobaric, right? Constant temperature. What else do we have? constant entropy, right? Adiabatic, right? Okay, so this is adiabatic, meaning that there is no heat input, right? Okay, so that is it. But is this isentropic as well? Is the compressor state isentropic? Or we can back up a little bit. What does an isentropic process mean? Reversible, which means that a reversible process is a process in which you don't have any change in what? Guys, come on. You should be able to answer this, right? What? Entropy is constant. And next question, someone else please answer.
I also thought, usually in the diagram, doesn't 2 go straight up to 3?
Okay, that's a good question. So it means that entropy is not constant here, right? So in a compressor, in a real world compressor, not an ideal one, in a compressor we don't have an isentropic process. It's just an adiabatic process, right? And that essentially means that, as Ryan mentioned, in an ideal case, you want to go from 2 straight to 3, right, without adding any entropy to your system. That means we have to focus on the deviations from the ideal case when we are analyzing the cycle, a turbojet cycle, a jet cycle in general, right? That deviation is very important. That's why when you are doing the cycle analysis, hopefully you have done like Rankine cycle analysis, right? You have done Rankine cycle analysis in your thermodynamics or Carnot cycle analysis. You have seen that we are very concerned with the efficiencies. Okay, so just let's move on a little bit. We'll get back to this discussion because we have to talk about each component separately, and you have to engage in the discussion. That's very important for me, as you guys know. But what are the design parameters when you're dealing with a gas generator or a jet engine in general? The compressor total pressure ratio, pi of C, and the compressor stages are a very important design parameter, as well as a host of other design parameters like the turbine stages, the diffuser condition, the inlet condition, the nozzle condition at the exit, right? Okay. Well, one question I have for you guys is this, before moving on. Is there any situation that makes the use of compressors redundant, essentially, unnecessary? Not you. Right? I appreciate your engagement, though. I really appreciate it. But I want to make sure that everyone else is also able to answer the question. Let's start with Tyler. Okay, why don't we use ramjets in general, right? Why don't we use compressor in a ramjet then? Okay, what's going to happen when it's coming in at a high speed? What is the goal of a compressor? Do we want to increase the speed, or what do we want to do? Let's go to Anna Victoria and see if she has anything to add. All of you should jump in. I shouldn't go one by one.
I like to talk. No,
Let's go. Let's everyone. There are only 5 people, so I don't have to beg you guys to say something, right?
I would have also said
We're all going to say the same thing. But also, if you have oxygen provided through chemical means, it's no longer like we're not talking about a jet anymore. We're talking about a rocket engine, and you don't need compressors.
Ah, okay. that was a good example. That's not what I had in mind. But yeah, that's a good example. Rockets. Do we need compressor in a rocket? Yeah, that makes sense, yeah. Okay. So, but let's go back to the ramjet, right? We are talking about the jets. We are talking about a gas generator, right? Which means that we are not talking about like liquid propellant or anything else. So Anna Victoria or Neela, do you guys have anything to say? So is there any situation that makes us needless of using the compressor?
Ramjet?
The type of jet you want, you don't need to use a compressor in is a ramjet. But my question is, why don't we need to use a compressor in a ramjet?
Compressor, all it does is it takes the air in, compresses it, and that increases the pressure.
That's the idea of a compressor, yeah.
And a ramjet, I'm not too familiar with that.
Okay. Let's go to Ryan.
Well, the inlet's designed in a way that it induces the shock waves in a way to create pressure across like the shock wave, so you don't need an actual mechanical thing.
So exactly. So supersonic flow. That's the general answer will be in a supersonic flow, because you can manage the flow with shock waves. You won't need to include a compressor, right? But what it means is that you cannot use these supersonic jets, ramjets, in a subsonic condition, right?
So ramjet means supersonic jet?
Ramjets are used in supersonic flow, but ramjet, the ram part refers to the ram pressure. The ram situation that's coming. Okay, but we'll talk about ramjets later on. But what I want to hear from you guys is the supersonic condition because of the shock waves. Okay, so we have the design parameters that we need to take into account when designing a gas generator or a jet in general. We have the compressor pressure ratio, we have the compressor air mass flow rate, we have the combustor fuel flow rate, and also the fuel heating value and the all of the component efficiencies. Our focus in this chapter is mostly on the component efficiencies. Okay. So moving on from a gas generator, we want to talk about a real engine, a real turbojet engine. Right? As you recall, a real turbojet engine has different components, right? And we number all of those components. Number 0 is going to be your ambient, 1 your inlets or your diffuser inlet, let's say, 2 your compressor inlet, 3 your burner inlet, 4 turbine inlet, and 5 turbine exit. 9 is going to be your final exhaust of the engine. So, I want to go over each component one by one. Let's start with the inlets. Let's start with the inlet, okay? The job of an inlet is to deliver the air to the compressor at the right Mach number and the right quality. So I just want to make sure that you guys are clear that these are the numberings we are going to use for each stations, because I remember some of you got confused before. And this is the numbering everyone uses. It's not just us, right? And so essentially it is charged with decelerating the air from a Mach number, the ambient Mach number, to the compressor Mach number, as we said. So it is doing a diffuser job. Right? It is diffusing the air. When you have flow deceleration, it means that you have a static pressure rise, which means means that you have adverse pressure gradients, and also you always have the viscous effect, the bilayer effect, where you may encounter some flow separations in a diffuser. What does it mean when you have the flow separation? What does it mean for your process? What kind of a process do we have here? Is the flow adiabatic? So our main focus at the thermodynamic process that we are always interested in this course, and in propulsion in general, or in aerodynamics in general, is an isentropic process, right? How something compares to an isentropic process. So when I ask you what will the process look like, you have to essentially explain to me whether it's an isentropic or not, right? So is this process an isentropic process? To find out whether something is a process is isentropic, you have to investigate whether it's adiabatic and reversible, right? So is this process adiabatic? Yes. Is it reversible? No. Why not? Because of the friction, flow separation, and all of those other things, right? So the inlet process is in the real world is not isentropic, right? But in the ideal case of an inlet process for us the ideal case of an inlet process is an isentropic process. And because of the viscous friction, we always have some sort of a heat loss or energy loss to the boundaries. And you can actually simply use the Fourier's law to find the temperature gradient because of that friction loss, if you will. But your HS diagram is going to look like this. So we are going from station 0 to station 2, right? From the ambient to the compressor. So we are including the ambient to the inlet of the inlet in our analysis as well. So your ideal case would be to go from 0 to T2S, right? Isentropic case, right? Or to 2S, let's call it. You have 2S, right? Is there any questions here? The ideal case is going to go from here 0 to here to the isentropic case. Let's say this is the total condition. Go from the total condition 0 to total condition at the compressor, which is the isentropic. But what happens in reality is that you go from here to here, right? Which means that you have some entropy rise, right? This entropy rise means that we are going to encounter some total pressure loss, right? And we can find the total pressure ratio using the variation of the Gibbs law as a function of the entropy rise. But these are all the things that we have seen before. We are very mostly interested to find the inlet adiabatic efficiency, right? So based on this idea that our ideal process is an isentropic process, and in reality we don't have an isentropic process, how would you think should we formulate? How would you think we should formulate the efficiency? what is the idea of the efficiency, right? It compares your case with the ideal case, right? What is the ideal case? No, that's a cycle efficiency. That's a whole different. We are talking about one process going from 0 to 2, right? The idea is the ideal case is an isentropic, right? So what is the total? How do we characterize the total energy change in a process in general? We compare the total enthalpy, right? That's the energy change, right? So you define your efficiency as the total enthalpy at the station 2, then you have the isentropic process minus your total enthalpy at the station 0, right? The enthalpy at the station 0, divided by the real total enthalpy at the station 2 minus H naught, which is the enthalpy at the station 0. Okay, so is this value, so we are essentially dividing the ideal case by the real case, right? Is this value larger than 1 or smaller than 1? Why larger? That's what I'm getting at. So you actually are on the same page as them. So you think this value is going to be larger than 1, right? Okay. Who else agree with them? No one else? Is it no one else or everyone else? Let's go with Joshua. What do you think?
I'm in the middle of something right now.
Okay.
I'm sorry.
That's he's in the middle of something, in the middle of a class. That's all right though. Let's go with Tyler.
So just to clarify, we know what is
Don't look at the velocity. Just look at this one.
Can we go back to the graph?
Okay, that's the best answer, right? You always characterize your efficiency to give you a value of less than 100%, right? Or less than 1, right? So you always formulate your efficiency in a way that will give you a value smaller than 1. Okay? So we are going from 0 to T2S, right? Your HT2 is always larger than or equal HT2S, right? Why is that the case? Because in your inlet you have a huge static pressure rise, right? In your ideal case, you won't have that huge rise, right? Does that make sense? So the ratio, the efficiency definition in an inlet, in a diffuser, looks a little weird. It is not ideal. It is ideal over the real case because your total enthalpy will end up being larger than your ideal case, right? So the difference between 0.0 and 0.2 is going to be larger than the real case, right? Is this clear? Okay, so to play with the formula, we can always play with the formulas, as we have seen many times before. Let's divide everything in this formula. Let's divide everything by H naught. When you divide everything by H naught, you can simply replace this H2S and H naught with CP T2S and CP T naught, right? CP's will cancel out, you will get this formula, this ratio, and we don't actually touch this that much, but we already know that HT naught, meaning that the total enthalpy is going to be okay, are we clear up until this point? Yes? Okay. So we can replace HT naught with HT2, and then we replace it. This is an isentropic process. We use the isentropic relationship for this, and this is an equation we have seen in chapter 2 that relates the enthalpy ratio, the total enthalpy ratio to the Mach number, right? You remember that? So we do this replacements, and yeah, we can rearrange the equation, and that will give you the pressure ratio. That's going to be your inlet, your diffuser exit. I'm going to call the inlet diffuser, not to confuse the inlet and outlets, right? Yeah, that's going to be giving you the total pressure of the outlet over the ambient pressure, which is equals to the efficiency 1 plus the efficiency of diffuser multiplied by gamma minus 1 over 2, and naught squared to the power gamma over gamma minus 1. This, the total pressure ratio is actually called the total pressure ratio between the two stations is actually called the total inlet total pressure recovery. Let me go back to if you haven't written it. Pardon me? That is not going to help us. You know why? Because that ratio cannot transform to pressure, can it? Yes or no? Why not? Okay, so that's actually that's good that you asked that question. We transform this temperature ratio to a pressure ratio. And this time it is Josh's turn to answer my question. It's actually because you're on your phone, you have to answer the next 4 questions. Okay? That's your punishment. Huh?
That's fair.
Yeah. It is not fair. It is actually a lot less. The punishment should be harsher. But okay, so how did we get from this temperature ratio to this pressure ratio? Is this kindergarten?
Because it's adiabatic.
It is what?
It's isentropic.
It is isentropic. Thanks, Ryan. But I'm pretty sure Joshua knew it. You don't need to. So then the next question is, why didn't we do this for this ratio? It is not isentropic. Right? So that T over T wouldn't give you any pressure ratio, right, to the polar whatever, right? We wouldn't have any equation for it. Does it make sense? Okay, so, and I mean, eventually, the goal was to relate this pressure ratio to a Mach number. That was essentially the goal, using the efficiency of the diffuser. So here, in this condition, we are talking like this part, right? 1 to 2, right? But we have included 0 in our analysis, right? So we go from 0 to 2. So this whole thing is going to be your inlet diffuser, right? The whole thing from 0 to 2. So whenever you see 0, it means that air is coming in. Whenever you see 2, air is going out. But it's not going to be the same thing when we are dealing with the compressor. Where you are dealing with the compressor, when you see 2, air is going in. When you see 3, air is going out. Okay? Okay, so we define the total pressure recovery as PT2 over PT naught. And then we want to use that total pressure recovery in our formulation. So we multiply and divide whatever we have with the PT naught and divide by PT naught, right? To get to the definition of the total pressure recovery, which was this, right? The total pressures, of course. You plug that in and you play with the equation. This is what you're going to get for your pressure recovery, total pressure recovery. So your total pressure recovery is related to your diffuser efficiency, and this is a diffuser total pressure ratio or recovery. Since we are dealing with total pressure, we're going to call it, let's call it pressure ratio, doesn't really matter. Your diffuser total pressure ratio is going to be related to your efficiency, the Mach number, that's the ambient, the flight velocity, right? And the total pressure, the flight total pressure to the flight static pressure, okay? And we already know this relationship is going to be 1 plus gamma minus 1 over 2 and naught squared. We already have this relationship, right? And this is going to be, we also can replace it with pi r, which is the ratio between the total pressure and the static pressure. This can be a design parameter, but we don't really care about this equation that much. The equation that you need to concern yourself with is this and this, these two, the first two. Is there any questions? So there are a lot of, when you're dealing with efficiencies, there are a lot of equations. You just have to make sure you understand the equations. Like, I remember when I was taking this class a long time ago, I was confused about the inlet efficiency myself, right? And that's the reason I'm focusing on it, because my professor then didn't focus on it, and I actually did drawing in the exam, right? Okay. So the question I have for you guys, the next question that you want to answer, that this is the last question you want to answer, is dealing with inlet. So the idea was we want to calculate the efficiencies. We have calculated the efficiency for the inlet diffuser, right? But then let's talk about another situation that we haven't dealt with. What will happen when you're dealing with a low speed or takeoff condition? When we are dealing with a high speed, when you are dealing with a high speed condition, let's say this is your inlet, the stream tubes are going to look like this, right? So the area is going to increase. That was the idea, that's the idea, right? From 0 to 1. Right? But what's going to happen when you are taking off or at a very low speed flight? Huh? You have the opposite effect, meaning that your area is going to decrease. So you are going to have an acceleration instead of a deceleration. And we need to have the same thing happening inside the inlet as well. So the inlet, in a very low speed condition, your inlet is going to become a nozzle. right? And we have to make sure that we can accommodate that condition, right? It is going to act like an other design. That's why in the design, in the design, this is something that you always see, the bell mouth inlet. You see a lot of times, right? That to accommodate for this condition, for the condition of the takeoff or very low speed. Any questions? And always keep in mind that let's do this. I should have told you this. Let's actually talk about it a little bit, and then we can move on to the next one. Why are we doing this? Why are we calculating the efficiencies? Right? Why is the efficiency important? What do you want to get out of this? Start with Joshua.
Is that talking like more design? What are we talking about for efficiencies? Are you talking about calculations?
Calculations. I mean, design and calculations should go hand in hand, right?
Yeah. But so for efficiencies, then you want to have a more efficient engine using less fuel.
Yeah, that's correct. But let's say you already have the inlet. You're calculating the efficiency for that inlet to do what? Is this clear what I'm asking? I'm asking for your opinion, so even if it doesn't really matter if it's not clear.
So if we already have the inlet and we're trying to calculate the efficiency of that inlet, what the goal is?
What is the goal? Let's say you have calculated the efficiency of the inlet. Why do you calculate it? Why do you care about the efficiency?
To know like how much air is going through your compressor.
Okay. And what do you want to get out of that? Eventually, what is the end goal here? Let's say we are doing a cycle analysis. What do we do when we do a cycle analysis? Okay, eventually, in some cycles, you want to calculate the amount of energy produced, right?
Talk about those graphs,
Which graph?
the ones that we were talking about from 2 to 3 to 4 to 5.
That's your cycle, right?
So yeah, those graphs, they discuss entropy, they discuss temperature, pressure.
Okay, these are all correct. But why do we do a cycle analysis? Why do we find the entropies? Why do we find the efficiencies?
He was talking about the compressor, and he said, what was the end goal of the compressor?
In general, what is the end goal of a combustor? What is the end goal of a turbine? What is the end goal of this?
You get more thrust.
You wanna
Produce energy.
do we wanna produce energy with a turbojet?
I guess much more power.
So essentially, you want to do you have anything to add?
Only thing is just to increase the efficiency of the entire engine.
Okay. Do you have anything to add?
See that increase the efficiency of the most added.
Okay, so that's actually the reason I want to bring this up is because a lot of you guys usually complain that we have too many formulas, right? Not a lot of you guys. I've heard this complaint from one person, which is a common complaint. And the fact that I haven't heard it from you doesn't mean you don't complain about it, right? And so the reason we have all of these equations and all of these mathematics is that eventually, as a jet engine engineer, you want to be able to calculate the thrust, right? You have to be able to calculate the thrust of an engine, right? You have to be able to calculate the temperature at the combustor because you want to make sure when you are designing it, it doesn't go over the temperature limit, right? If you don't have these efficiencies, if you don't have these formulas, you won't be able to do any of that calculation, right? So in real world, you may end up not being a turbojet engineer, right? Some of you may become a turbojet engineer, but that's beyond the point. But in real world, if you ever were to design or to analyze an engine, you have to do a cycle analysis. You have to use all of these formulas. You have to calculate all of the efficiencies and everything else, right? So you have to make sure that you know the formulas, you know how to write an energy conservation for different components and all of the cycle, right? So you have to be able to understand the cycle of an engine in and out, right? Does this make sense? So I wanted this to be the introduction to the inlet analysis. But eventually the point is, if you didn't understand why an equation exists, you have to make sure to ask, right? Because sometimes this equation, not just to me, to any of your instructors, they either already make sense to me and I already know the purpose, right? Which I probably won't explain to you because it's very obvious to me, right? Or I don't know the purpose. Then if you ask me, I will go out and find, right? What is the purpose of this equation is here. Does this make sense? Okay. So, moving on, a summary of the inlet. Inlet flow is adiabatic, which means that your total energy, your total enthalpy doesn't change. Inlet flow is always reversible, irreversible, sorry, always irreversible, which means that you have a total pressure loss. The important concept in the inlet analysis in the design is the efficiency of that diffuser. And when I say inlet here, I'm talking about the diffuser. So all of the inlet diffuser, right? Not just one station. The efficiency, the pressure ratio, the diffuser pressure ratio, and the diffuser efficiency. In the cruise conditions, your A naught, the stream tube area is smaller than the diffuser outlet or the inlet outlet area, but in a low speed or a takeoff condition, you have the reverse condition, so your inlet is going to act like a nozzle instead of diffuser. You want to accelerate the flow. And the geometry of your inlet is very important when you want to do an external aerodynamic analysis on it. And it becomes very, very important actually in higher angles of attack when dealing with the installed performance. Is there any questions? Okay. So let's try solve an example together. Let's try solve an example together. Let's try to solve this one. And it's telling us an aircraft is flying at an altitude where the ambient static pressure is 10 kilopascals. And flight's Mach number is m0.85. The total pressure at the engine face, meaning at the compressor engine, which is the station 2, is PT to 15.88 kilopascals, and we are assuming the inlet is adiabatic and gamma is 1.4. And we are asked to calculate pi of D, or your pressure recovery, or the total pressure ratio. How would you go about doing that? What was the pi of D? So you're talking about this equation, right? Yes? Okay. Can we use this equation here? Do we have the eta? But in all of its other forms, we still have eta, don't we? You calculate what? Isn't it easier to calculate the total pressure at the station 0? Okay, let's do that then. We have the pressure ratio, the total pressure ratio, right? Pardon me? uh, you do need an isentropic, that's right. But we have this equation for the total pressure ratio to the static one, right? 1 plus gamma minus 1 over 2 m naught squared, right? And to the power gamma over gamma minus 1. So we have the P naught, we have the m naught, we have gamma. You should be able to find total pressure, right?
But isn't, that's supposed to be PT2 over PT naught, or?
Pi of d, yep. PT2 over PT naught, yep.
Don't you need the A to D in that formula too? I think when you gave it to us, it was 1 plus.
No, this is a very old formula. This is the pressure ratio. This is PT naught over P naught. That's the pressure ratio.
You already have it, all we need to do that is, you have the 10 and the 15.8.
10 is P naught.
P9, and the other one is.
PT2.
PT2.
So you don't have the PT naught. And pi of d is defined as, these are very important. You have to make sure that you are,
For that equation, don't we have everything that we need to calculate for data, for efficiency? We have PT2, we have P naught. The Mach number.
yeah, but the first part is asking us to find the pressure recovery, right?
Couldn't we do B first and then go back to A?
I thought this is going to be easier, but yeah.
But that equation for PT naught over P naught,
That's just a regular, yeah, that's just a regular equation.
You can easily just find that with that S.
Yeah, yeah.
So there isn't like you can use both the eta formula we got and just the simple PT2 or PT0, like you can use either based on the data.
Yeah, both of them are valid equations, right?
Yeah.
Why not? So, how would you go about calculating? Did you have another question? No. How would you go about calculating the efficiency then? Which equation would you use? You actually, to answer your question, you should definitely, even after calculating the eta, you should definitely find PT naught, right? Because you don't need to use this equation.
That's how, I'm just saying how I would have solved it.
And maybe if you come with the correct answer, you can use any equation. We have millions of equations. That's
Can
right.
I see if I get it?
Pardon me?
Can I see if I can get the same answer?
Yeah, definitely after class, of course.
So now you can just solve for eta using the bottom equation.
Yeah, or this one, right? Which is the same thing, just a reformulation. That's it. And then you get the eta, and then the third part of the third part is asking us to find the non-dimensional entropy rise caused by the inlet. The non-dimensional entropy rise is delta S over 1. So how would we do this? It is, if you go back to your equations, it has a formula that related the delta S over R, or related delta S to natural log of pressures and natural log of temperatures, right? Or, yeah?
It's PT2 or PT9 equals either there or delta S over 1. That's total pressure also.
That's the total pressure. That's correct. Okay, so we have an adiabatic. The temperature terms go away. And you essentially means that you can use the pi of d, your pressure recovery, right, to find the entropy rise.
So, the inlet efficiency was the
E squared ideal, or that's actually, you don't, you shouldn't use that formula. That's just there for concept.
Yeah, but yeah, that's the adiabatic efficiency,
The efficiency, you have to use this formula. We talked about it, right?
So yeah, well, I have it here that the B is also equal to the change in amplitude.
Pardon me?
And the change in amplitude is
Guys, don't write this equation down. If you have written this equation, just erase it. Okay? If you think it's going to confuse you.
no.
The velocity equations, you don't use it, right? We don't calculate any ideal velocities.
I just need to go down to that,
Okay. Is there any questions about the inlet diffuser? Or inlet bed inlet? No? Let's move on to the compressor. The first thing you need to know about a compressor is that the compressor requires external power to operate. But the question is why? Why does the compressor need external power to operate? It actually can, right? You can have the blades in a way, configured in a way that, like a wind turbine, right?
Would you wanna,
The blade is turning on its own, right?
would you wanna be able to have control over the speed, like just in general, so that the air isn't going like, so it's at the right condition? Like
Let's say you don't need the control. Let's say control is all of the equal. You don't need to control the speed.
So it needs external power in order to start to function?
No, it doesn't need extra. It needs external power.
Then you would need external power in order to
In order
start
to-
the process.
Not the start. To do the. What is the job of a compressor?
takes in air, compresses it,
To compress air, right?
and the pressure rises, and that provides the force for your thrust.
Oh, but you're saying without the external power, so you're implying that the external power is coming from the turbine at the end of the engine?
I'm not implying it. But it is coming from the turbine, right?
Yeah.
That's the idea. That's the idea.
And without the external power, you would just have reverse flow back out of the compressor, no?
Because of the turbine?
No, without the turbine, if you compress the air, and then you didn't have any external power continuing to compress the air, it would just backflow back out, because you'd have a pressure gradient.
Okay, that's how you're okay.
The turbine compresses air as well, so a little bit of it here, doesn't it?
Turbine compresses the air.
Well, it takes the air in, and in the process, there's does somewhat get compressed, and the compressor just compresses.
That's a very good thing that you brought up. That's the reason I'm asking this question.
So yeah, you need to turn it on, so the turbine spins, right?
No, that's not the answer that I'm looking for.
I don't
No,
understand.
I'm not talking about the starting condition. And okay, so do we need external power for turbine to operate?
So what do you mean by external power? Are you talking about?
It's very obvious. External power. Like let's say you need a battery for it to operate. But external power.
So you need fuel.
Fuel. Not fuel. I mean, like let's say you have to rotate a shaft with your hand, right? This is not. Your fuel is food, right? You definitely need fuel to be able to rotate the shaft. But for a compressor, you need to rotate the shaft to compress the air. Do we need to do the same thing for a turbine? Do we need to rotate the shaft for a turbine to operate?
No.
Yes?
I say no.
No. Yes, no. Turbine.
Turbine, you need to rotate the shaft, I'll say yeah.
No. So we have 3 no's, 1 yes. Go ahead. What is your?
Very confused with what's going on.
Yeah.
So
Okay.
I know compressor requires energy in order to.
That's just because. Okay. Just wait a second. I guess you guys have engaged a lot.
have to
The thing is, some of you say the wrong things. They continue with the discussion.
Let me just throw this out there, area, it plays with area.
Yes. Wait a second. Just wait. Don't say anything. Right. What is the job of a compressor? To compress air, right? What is the job of a turbine?
To run to provide.
To what?
To provide power and like.
To provide power, right?
and run the
So, if the job of a turbine is to provide power, right? And you're telling me that power, let's say that power goes to a rotating a shaft, right? If I need to rotate the shaft myself for turbine to work, doesn't it contradict the definition of the turbine, right? Turbine is supposed to rotate the shaft, right? If I rotate the shaft for turbine to work, it means that it is not a turbine anymore, because it is not generating energy or power, right? Okay. The compressor is essentially the same thing as a turbine, but it works the other way, right? It requires energy, so I need to rotate the shaft for the compressor to work, so it can add the energy that you are giving to that shaft to the air, right? So you are increasing the energy of the air. Does this make sense?
So the answer was yes to rotate the shaft.
Not for the turbine. No, the answer was no. The
compressor requires power from the turbine in order to operate. External power is the turbine. The turbine does not. You need to start the turbine using external power.
You're talking about the starting. I specifically said from the beginning that we are not talking about the starting condition, right?
That was my fault. I said starting condition.
Yeah, but I said no, right? Okay. Are we clear now? So turbine is actually getting the energy from air to give that energy to a shaft, right? Compressor is getting the energy from that shaft to give it to the air. Okay. I didn't think we would talk. Okay, that's good. That's good. So the compressor discharge contains higher energy gas. That's the only answer I really needed. For whatever reason, you guys were I don't know. I don't know why you couldn't answer this one.
I do remember somebody bringing up fuel.
Wouldn't it be the combustion?
See. This fuel doesn't have anything to do here. You made this comment.
Battery.
You made this comment. And just forget it. Fuel doesn't have anything to do with this.
So what do you mean by energy gas?
Energy is the same as fuel.
No, energy is gas. Is that something in that? Are you meaning air as gas?
Higher energy gas. So gas is going out with a higher energy. Whatever gas is in there. In our case, it is usually air. Okay. But yeah, that's all right. Let's move on. So what kind of process do we have? We are adding energy with compressor. We are adding energy to your system, to the air, right? Is it what kind of process do we have? Is it adiabatic? Yes. Why? There is no input heat. That's it. There is no heating happening. Well, is it isentropic? Is it isentropic? No, why not? Pardon me?
When the static pressure rise across like compressor blades and cause total pressure loss.
Okay. The static pressure, why does it rise? Why does it change though? So to answer whether a process is isentropic, you have to make sure whether it's adiabatic and reversible. Is this process reversible? No, because of the wall friction and all of those frictions that are happening. The frictions are always there, right? So it is an irreversible process. But what are the efficiency parameters that we need to focus on in the compressor? There are actually two. First one is the compressor adiabatic efficiency, eta of C, standing for compressor. And the next one is the compressor polytropic efficiency, E of C. Okay? Let's move on. And since this is not an isentropic process, the temperature ratio of a compressor, which is the tau of C, right? We define the temperature ratio as tau of C, is, so whenever you see a tau, it is referring to a temperature ratio. And whenever you see a pi, it is referring to a pressure ratio, right? You just have to make sure that you are clear on that. It is not an isentropic process. So this equation, the relationship between the temperature and pressure ratios does not hold true here. And your HS diagram usually looks something like this. Your ideal case is not to have any of the friction losses, right? If that was the case, you would have had the isentropic case, the reversible case, or the isentropic case. That would be the ideal power required to compress any amount of, like that specific amount of air, right? But the actual power you're going to need is going to be higher. It's going to be different, right? It's going to be at a higher entropy and as well as a higher enthalpy. Keep in mind that this is actually the first stage of a gas generator, right? The gas generator only has compressor, burner, or combustor, and turbine, right? Turbine. Okay, so how do we calculate the efficiency here then, based on what you see? Exactly, it's going to be the same thing as the last time, yeah. So you're going to be your isentropic versus your actual. And this value is going to become smaller and smaller as your T3, as the total condition 3, moves on this line, and this isentropic line. Okay. This time, we are going to divide everything by HT2, which is the inlet of the compressor, right? And we are going to replace that with the temperature ratios. Okay. The first temperature ratio on the top follows the isentropic relationships. So we can just replace it with the pressure ratio, and the pressure ratio is going to be the pressure ratio of the compressor. So at station 3, your total pressure ratio with the isentropic process is going to be the same as total pressure ratio without the isentropic process. So it doesn't matter whether your process is reversible or not, your total pressure ratio change. Your total pressure ratio is going to change the same amount. Well, meaning that we can't use the pi of C to replace this temperature ratio. Okay. But what can we do for the denominator here? What is this? We didn't do this in the previous case, mainly because we didn't have the temperature ratio definition, right? But this is the definition of temperature ratio of a compressor. So we can actually replace whatever we have with a temperature ratio. So the efficiency of a compressor is a function of its pressure ratio and temperature ratio. Okay, any questions? So far we have talked about the adiabatic efficiency of a compressor, but we need to talk about another type of efficiency, which is a polytropic efficiency, right? The polytropic efficiency is defined as the derivative of your enthalpy, isentropic total enthalpy, divided by the derivative of total enthalpy, regular total enthalpy. So as you can see, the difference here, the difference between the two is going to be this derivative, right? Over there, in the previous definition, we are taking the difference at the beginning and the end, right, between the inlet and the outlet. But here, we are focusing on the small amounts of changes that is happening inside a compressor. The main reason we have this is actually called the small stage efficiency. The main reason we have this polytropic efficiency is because a compressor is made of different stages, made of different blades, right? So efficiency of each stage can become important in your analysis, right? So you have to make sure that you understand the polytropic efficiency or the small stage efficiency as well. So yeah, just compared to the definition of the adiabatic efficiency, which essentially this one is delta, so the macro scale analysis, this one is a differential scale analysis, right? So that one is an integral scale analysis and differential scale analysis. Okay. So we have the equation. If you go back to your chapter 2, we had this equation that related the enthalpy to pressure, density, and temperature and entropy, and all of them together, right? Which means that we essentially can replace dH of T, your total enthalpy, for here, we can replace dH of T with the rearrangement of this equation, but we can also rewrite this equation for a reversible process, right? So what are going to be the changes in enthalpy, changes to this equation that I'm showing here when you are in a reversible process?
It's constant, so it'd be 0.
ds is going to be 0, right? So this whole thing is going to be equal to 0. You can move this to the other side and you can get to this equation, right? So the changes of the reversible total enthalpy is going to be equal to the changes of total pressure divided by density. Okay, so let's rephrase that. Essentially what we have done here is that we have replaced the isentropic total enthalpy change. We have substituted this equation with that isentropic. We have put this in there, right? And then we have used the ideal gas law to find to write the density as a function of pressure, temperature, and also the gas constant. Now we have played it a little bit. This is what you are going to get. Okay? Does this make sense? So essentially, play it a little bit. We have the definition of enthalpy. And when we assume Cp is constant, it's going to be Cp dt, right? So we replace that here as well. We put the definition here as well. We can have the equation for the small stage efficiency or polytropic efficiency as a function of the changes in total pressure versus the changes in total temperature. Okay, over the total temperature of the initial condition. of the initial stage. Does this make sense? Okay. Which means that we can actually, if you recall, let's go back here. If you recall this, it's all lost. This meant that the isentropic relationship is not true here. Right? The temperature ratio and the pressure ratio. And for the online people, I'm talking about this first equation here. You don't see it, right? Do you see this? No, that's all right. Like about the first equation, the temperature ratio is not equal to the pressure ratio to the power gamma minus 1 over gamma, right? That's because it is not an isentropic process. But when you come up with this definition for the smallest stage efficiency, you can just rewrite this, okay? Take the integral, and you don't need to go over that process, but eventually we can relate the temperature ratio to the pressure ratio using the polytropic efficiency, right? So that's the whole idea. It's not the whole idea, but it's one of the main uses of the polytropic efficiency that gives you the relationship between the temperature ratio and the pressure ratio where you didn't have it before, because it is not an isentropic process. And you always have to keep in mind that you can actually, using that equation, you can conclude that your temperature ratio, your real temperature ratio, is going to be always be larger than your isentropic temperature ratio, which means that your final total temperature is always higher after the compressor, after the compression stage is done. Your final total temperature is always higher than the isentropic total temperature. And yeah, we went over this. Let's stop here, because I have a feeling like we are at the end of the class, so it doesn't matter how I feel. So we are going to continue this discussion